how to calculate logarithms in your head. So the first thing you need to know are the logarithm identities. For example, the log of a times b is just the log of a plus the log of b. Same goes for when you're dividing numbers. Log of a divided by b is log of a minus log b. When you raise a number to a power, a to the n, then the log of that is n times the log of a. And finally, the log of 10 is 1 because we're working in log base 10. All right, so if you want to calculate the log of a number, like log of 60, one way to go about doing that is to factorize the number. So you can break down 60 into 2 to the third times 3 times 5. And using the log identities that we had on the a little earlier on, log of 60 is just 3 log 2 plus log 3 plus log 5. So it might occur to you that if you were to know the log of 2, 3, and 5, or the log of prime numbers in general, if you want to calculate the log of a larger number, you could factor it into its primes, memorize those primes, the log of those primes, and then add them back together. So in this case, log of 2, 3, and 7 are 0.301, 0.477, and 0.845 respectively. But what about log 5? I didn't include that prime number here. Well, we can get log 5 quickly from the log of 2, so don't even bother memorizing it. The log of 5 is just the log of 10 divided by 2, which is log of 10 minus log of 2, which is 1 minus 0.301, or 0.699. So as long as you know log of 2, you can quickly get log of 5. Not worth memorizing log 5. So it's worth memorizing probably log of 2, 3, and 7, and I also listed a couple more here, log of 1.1 and 1.01. I'll tell you why in a second. So for every 1% that a number increases, well, if a number increases by 1%, that's equivalent to multiplying it by 1.01, and then if you calculate the log of that number, you can factor out that 1.01. So by multiplying a number, or by increasing a number by 1%, it's equivalent to adding into its log the number 0.0043. And similarly, for every 10% that you increase a number, its log increases by 0.041. And then also the same, or the opposite things happen when you decrease the number. If you decrease the number by 1%, its log decreases by 0.0043. And for 10%, it decreases by 0.041. Now this is useful because small changes add up linearly. For example, if you have a 3% increase in a number, that's almost equivalent to 3 consecutive 1% increases. So if a number increases by 3%, then its log will increase by 0.0043, and then again, one for each of those 1% increases. So if it increases by 3%, that's equivalent to its log increasing by 3 times 0.0043, or about 0.013. So we have these primes, 2, 3, and 7, that we memorize the logs for, as well as these estimators, this 10% and 1% estimator. So we have 5 numbers now to memorize. Let's do some examples. But before we get to that, it might be useful also to forget the decimal places. 0.301, let's just call it 301. We'll just multiply everything by 1,000 while you're calculating the log, and then take that back into account at the end. All right, so here are the examples. Let's do log of 63 first. So 63, this is a pretty small number. It's 9 times 7, or 3 squared times 7, so you can prime factorize it pretty quickly to 2 log 3 plus log 7. And now log 3 is 0.477, but again, let's just drop the decimal places and call it 477. So we have the log of 63 as, we're calculating it as 2 times 477 plus 845. Now, if you want to multiply 2 times 477, it could be a little tricky to do in your head. There are some tricks to doing this. One way to do it is to know that 477 is 500 minus 23. So you want to multiply that by 2. That's like 1,000 minus 46, which would be 954. There are different ways to add numbers quickly in your head, but that's kind of a prerequisite for being able to calculate these logs, because you're really turning these multiplication problems into addition problems. Anyway, that's about 1799 is 2 log 3 plus log 7, but if we put the decimal place back in properly, it's 1.799. And this is pretty close to the actual log of 63, so we're correct to 3 decimal places. The other example is log of 475. So you could prime factorize this by knowing that 475 is 5 times 95, and 95 is 5 times 19, and it gets a little messy. So with some numbers, it's more useful to do this approximation method using the estimators, the 10% and the 1%. So 475 is, well, that's 500 minus 25, so it's 5% less than 500. And log of 500 we can calculate pretty quickly. It's log of 1,000 divided by 2, or just simply 3 minus 0.301, or 2.699. Great, so we've got log of 500. Now if we want to do a 5% decrease, it's equivalent almost, it's approximately equivalent to 5 1% decreases. and each 1% decreases the log by 0.0043. So 5 of those multiplied out, it's about 0.022. So the log of 475 is this log of 500, 2.699, minus this 5% correction of 0.022, and we get 2.677. And that also winds up being correct to 3 decimal places. So you can see it with these 5 numbers, the log of 2, log of 3, log of 7, and then with these 2 estimators, 10% and 1% correction. You can estimate the log of any number on the order of about a couple of minutes, 1 or 2 minutes in your head with practice of addition of 3-digit numbers.